Hi everyone, this is our first video on notation. I'm going to be talking about molecular representations, or how we draw organic molecules, as well as the concept of functional groups. We have different ways of representing information about compounds based on how we draw them. One way of drawing a compound is just writing its molecular formula. This tells someone how many and what types of atoms are in that molecule, but it doesn't give you any structural information. You don't know how those atoms are attached together. As an example, let's consider a molecule with a molecular formula C2H6O. I know the atoms, but not the structure here. And I can actually think of two different structures. One possibility is you have carbon, oxygen, carbon. And in the other possibility, you have carbon, carbon, oxygen. In each of these structures, I have 2 carbons, 6 hydrogens, and an oxygen, but these are different compounds. Because they are not the same compound and they have the same molecular formula, we could describe these two compounds as constitutional isomers of each other. Another type of molecular representation that we've seen before is the Lewis structure. In contrast to just a molecular formula, in a Lewis structure, all of the atoms and bonds are drawn out. This gives us more information about the molecule, but it gets to be inconvenient once we start talking about molecules with more than 4 or so carbons. Here's an example Lewis structure for a 5-carbon molecule. Here I have the 5 carbons in a row and single bonds between them. Each carbon has hydrogens attached to it to give it 4 bonds total. As you write this molecule out in your notes, you're going to notice that it takes a fair bit of time to draw it out. A third type of representation is known as a condensed structure. Here, you don't draw out single bonds. What you do is you list the atoms in order of their connectivity. And although this is slightly faster than a Lewis structure, I still think that it's inconvenient once you have more than a few atoms. So I'll show you an example writing a condensed structure for the 5-carbon molecule whose Lewis structure is drawn at the top. The condensed structure here would be CH3, CH2, 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 CH3. You can see those groups if you walked down the same chain of your Lewis structure. I could even condense this even more if I wanted to. Notice that I have 3 CH2 groups in a row. Another option for my condensed structure would be to write CH3, CH2 in brackets, subscript 3 for 3 repeating CH2 units, followed by another CH3. The organic chemist's favorite style of drawing molecules is known as a skeletal structure, or sometimes called a bond line structure. These have a zigzag format, and each corner or endpoint of the zigzag represents a carbon. You save time and space by not drawing out hydrogens that are attached to carbons. And you assume that if a carbon doesn't have a formal charge, it has enough atoms attached to it so that it has 4 bonds total. So looking at our same 5-carbon chain molecule from before, here I've drawn the condensed formula. If I wanted to convert it to a skeletal structure, it would look like this. I've got my zigzag chain here, and each corner or endpoint represents a carbon. Here I've numbered those left to right, 1 through 5. And because you don't have to write out the C for carbon or draw out any of the hydrogens if they're attached to carbons, you save a lot of time writing molecules this way, at least once you get used to it. Now, I have a side-by-side comparison of different structure types for a molecule containing an oxygen and a nitrogen. We don't treat these quite the same as carbon. So here's an example Lewis structure where I have a nitrogen with 3 bonds, 2 of them hydrogens. I have 2 CH2 groups in a row, and then I have an OH group on the right. Each atom here has a complete octet. As a note, when you're drawing Lewis structures, always remember to draw out your lone pairs explicitly. If I convert this molecule to a condensed structure, it would look like NH2, CH2, CH2O. And my skeletal structure would look like a nitrogen attached to 2 corners representing carbons, attached to an oxygen. The carbon-hydrogen bonds are implied, but the nitrogen-hydrogen or oxygen-hydrogen bonds are not. Essentially, any hydrogen that isn't attached to a carbon needs to be drawn out. And in a skeletal structure, the lone pairs are optional. I haven't drawn them in here, but I often think it's useful to draw them once we get to organic reactions. So here I've drawn them in, 1 lone pair on nitrogen and 2 on oxygen. I want to show you what skeletal structures will look like when you have double bonds and triple bonds. Here's an example of a molecule featuring a carbon-carbon double bond. Knowing that each endpoint and corner represents a carbon, this is a 4-carbon molecule. If you want to figure out how many hydrogens are attached to each carbon, you have to think about each carbon as having 4 bonds total. That means that the carbons on the far left and the far right, numbers 1 and 4, have 3 hydrogens each, because these carbons just have 1 other bond to a carbon. And the carbons of my double bond, numbers 2 and 3, each have 1 hydrogen attached to them, to have 4 bonds total. We can also draw skeletal structures for molecules with carbon-carbon triple bonds. Here's an example of one. And these are going to look a little bit different than our zigzag structures. Importantly, a carbon is implied where the triple bond meets the single bond. So this is a 4-carbon chain, where 1 carbon is the end, the second one is where the triple bond meets the single bond, the third one is where the triple bond meets a single bond, and the 4th one is an end. We'll always draw triple bonds as linear to reflect the fact that the carbons of them have sp hybridization. Keeping in mind that each carbon is implied to have 4 bonds total, carbons 2 and 3 of my triple bond don't have any hydrogens attached to them because they have 4 bonds already, whereas the end carbons, 1 and 4, have 3 hydrogens attached to them because these carbons just have 1 other bond to carbon, and the rest of the 4 are implied to be hydrogens. You'll also see cases where the triple bond is at the end of a molecule rather than in the middle. Here I've labeled the 4 carbons of this molecule. Keeping in mind that each carbon has 4 bonds total, and ones that aren't shown are to hydrogens, carbon 1, which is only attached with a single bond to carbon 2, carbon 1 has 3 hydrogens implied. Carbon 2, which has 2 bonds, has 2 hydrogens implied. Carbon 3, which already has 4 bonds, has 0 hydrogens. And carbon 4, which has 3 bonds, has 1 implied hydrogen. going off of this theme of how many implied hydrogens there are, we're going to have to figure that out for carbons based on the carbon's formal charge. As I mentioned before, we're always going to assume that a neutral carbon has 4 bonds. So for example, if I look at this zigzag molecule, this has 3 carbons total, and this middle carbon has 2 bonds to other carbons, so it has an implied 2 hydrogens attached for 4 bonds total. Now let's consider a molecule with 4 carbons total, where we have a central carbon that is attached to 3 different outer carbons. If we looked at the inner carbon specifically, it already has 3 bonds to other carbons, so it only has 1 hydrogen attached. And if we look at an example where we have a central carbon with 4 different carbons attached to it, that carbon already has 4 bonds, and so it doesn't have any hydrogens attached. You have a different situation if your carbon has a +1 or -1 formal charge, and those carbons will have 3 bonds rather than 4. This affects how many hydrogens are attached to them. A carbon with a positive charge is going to have 3 bonds. It'll be sp2 hybridized, trigonal planar, and it'll have an empty p orbital. Here I've drawn a molecule where I have a +1 formal charge on a central carbon. This carbon has 3 CH3 groups attached to it. Because the central carbon already has 3 bonds and a positive charge, it does not have any hydrogens attached. If instead we had a central carbon with a positive charge attached to 2 other carbons, the central cationic carbon would have a 3rd bond, which is to a hydrogen. And likewise, if you have a skeletal structure with a cationic carbon with only 1 other group attached to it, that carbon has 3 bonds total, 2 of them being to hydrogens. We have a similar situation if you have a carbon with a -1 formal charge as well. These carbons will also have only 3 bonds. The difference in this case is that the carbon has 3 bonds and a lone pair, rather than having an empty p orbital, like the cationic case. For these negatively charged carbons, they have 4 electron groups around them, making them sp3 hybridized. If we ignore the lone pair and look at the shape just of the carbon and the things it's attached to that are atoms, it is trigonal pyramidal. And because it's sp3 hybridized, the lone pair goes in an sp3 hybrid orbital. So I'm going to show examples that are similar to those we saw for the cationic carbon. So let's first consider a case where we have a carbon in the middle with 3 other carbons attached, and the middle carbon has a negative charge. Because that carbon already has 3 bonds, it doesn't have any hydrogens attached to it, but it does have a lone pair, and I often like to draw out that lone pair because it'll be useful once we start our reactions later in the course. If instead we have a structure where a carbon has 2 other groups attached to it and a negative charge, that carbon in reality has 3 bonds, so it has a hydrogen attached that's not shown in the skeletal structure, and it also has a lone pair. And last, if you have a carbon with a negative charge attached to just 1 other group, that carbon has 3 bonds total, so it has 2 hydrogens that aren't shown in the skeletal structure, and the carbon also has a lone pair. I want to talk about when we're not thinking of carbon, how would you identify lone pairs, for example, on an oxygen atom? This is important in skeletal structures because, unlike Lewis structures, lone pairs aren't always drawn out in skeletal structures. So I'll show you a first method that's more rigorous, and then I'll show you a faster way of doing this as well. The first method is step 1, figure out how many valence electrons you have for the free atom. In the case of oxygen, this will always be 6. And second, determine if the atom in your molecule of interest has the correct number of valence electrons. If the oxygen in your molecule doesn't have 6 electrons around it, then it's going to have a charge. So let's look at this following molecule, where I have an oxygen with a negative charge, which is attached to a carbon, and that carbon is attached to 2 other carbons. And let's focus specifically on the oxygen with the negative charge. Oxygen always has 6 valence electrons. In the molecule, we're given the fact that oxygen has a -1 formal charge, and whenever you have a negative formal charge, you have an extra electron present. So in reality, we have 6 valence electrons plus our 1 extra one due to formal charge. So in this molecule, the oxygen has 7 valence electrons. The oxygen uses 1 electron to form a bond to carbon, but then it has 6 electrons left over in this molecule. Those electrons will pair up into 3 lone pairs around this negatively charged oxygen. A second method, which is faster once you practice it, is to just look for common patterns. And the patterns I'm about to show you on this page are specific to oxygen. The pattern is that if you have a negatively charged oxygen, it'll always have 1 bond and 3 lone pairs. So, for example, if you were given the following skeletal structure, where you have an oxygen attached to a carbon and another carbon, that oxygen has 1 bond, and then there are 3 lone pairs implied. In the skeletal structure, again, you don't always have to draw these. If you have an oxygen with no formal charge, it'll have 2 bonds and 2 lone pairs. For example, the 2 bonds could be a double bond to a carbon. The oxygen could be attached to 2 separate carbons, or your oxygen could be attached to a carbon as well as a hydrogen. In all of these cases, you have 2 bonds and 2 lone pairs because you have no formal charge on oxygen. And our last possible scenario is if you have an oxygen with a positive formal charge, that oxygen will have 3 bonds and 1 lone pair. Your 3 bonds could be to 3 different atoms, like a carbon, a hydrogen, and another hydrogen. Or the 3 bonds could be 1 double bond and 1 single bond, which add up to 3 total. Here as well, that oxygen, which is cationic, would have 1 lone pair. For nitrogen, there are different patterns because nitrogen is in a different column of the periodic table than oxygen, but we can still find trends for nitrogens with negative, neutral, and positive formal charges. If a nitrogen has a -1 formal charge, or is anionic, you could say, that nitrogen will have 2 bonds and 2 lone pairs. Your 2 bonds could be single bonds to different atoms, or it could be 1 double bond. In each case, it adds up to 2 bonds, and you have 2 lone pairs. If you have a nitrogen without a formal charge, it'll have 3 bonds and 1 lone pair. You could have different arrangements of bonds, like you could have a case where you have 3 different single bonds. You could have a double bond and a single bond, or you could have 1 triple bond. In each case, you have 3 bonds total, and the nitrogen just has 1 lone pair. And last, if you have a positively charged nitrogen, you could call this cationic. That nitrogen will have 4 bonds and 0 lone pairs. Here as well, we have different ways of getting 4 bonds. They could be 4 single bonds, a double bond, and 2 single bonds. Or one other possibility is a triple bond and a single bond. In each case, nitrogen is cationic, no lone pairs present. I now want to introduce the concept of organic functional groups. The functional group is a characteristic set of atoms or bonds that you find in a molecule. And it's useful to identify these groups because they'll often have predictable properties and distinctive behaviors. So being able to classify a molecule can tell you fairly quickly how it might react. I'll go through several examples on this slide and some later ones of names of functional groups, a general form of what they look like, as well as an example molecule. One functional group is called an alkene. This is going to have a carbon-carbon double bond. In my general structure, my R group could be a carbon or a hydrogen. A functional group with a carbon-carbon triple bond is known as an alkyne. Here, my general R group could be a carbon or a hydrogen as well. As a reminder, in terms of counting carbons in skeletal structures, remember that for the alkyne, where the triple bond meets the single bond is a carbon. And molecules where you have a carbon attached to a halogen, like a fluorine, chlorine, bromine, or iodine, these are known as alkyl halides. A molecule where you have a carbon attached to an OH group is known as an alcohol. The ether functional group will have an oxygen attached to 2 different carbons. A thiol is the sulfur equivalent of an alcohol. Here you have a carbon attached to an SH group. And what's known as a sulfide is the sulfur equivalent of an ether. Here you have a sulfur bound to 2 different carbons. An amine is a nitrogen with a lone pair and 3 bonds to different R groups, where R here could be a carbon or a hydrogen. An arene, sometimes known as an aromatic group, is a 6-membered ring of carbons where you have alternating single and double bonds in the ring. Here R could be carbon or hydrogen. Now we're going to get into molecules where you have carbon-oxygen double bonds. A ketone has a carbon-oxygen double bond where the carbon is attached to 2 different carbons. These have to be carbons, not hydrogens. If the carbon of your carbon-oxygen double bond is attached to a hydrogen instead, it's called an aldehyde. In terms of skeletal structures, keep in mind that the hydrogen of your aldehyde doesn't need to be drawn out, and that would make your skeletal structure look like this, but often you can choose to draw out that hydrogen, and I usually will, because I think it makes for a more attractive structure. A carboxylic acid is when you have a carbon-oxygen double bond with the carbon attached to an OH group. An acyl halide has your carbon-oxygen double bond attached to a halogen, which could be fluorine, chlorine, bromine, or iodine. An anhydride is a functional group where you have two carbon-oxygen double bonds with an oxygen in the middle. An ester is sort of like a carboxylic acid in the sense that you have a carbon-oxygen double bond attached to an oxygen, but instead of a hydrogen, the oxygen is attached to another carbon group. And last is what's known as an amide. Here you have a carbon-oxygen double bond where the carbon is attached to a nitrogen. I recommend making yourself a table of these functional groups and practicing with recalling them, either looking at the name and trying to draw out the functional group, and then likewise looking at the functional group and trying to remember the name. I promise with some practice this will get to be second nature. So to recap, I talked about different ways of drawing organic molecules and focused a lot on the skeletal structure, which is what we'll be using for most of the rest of the course. I introduced the concept of functional groups and drew out a table of examples of these. That's it for this video. I will see you in class.